Hi students, it's Ms. Brinkman, and in this notes video I'm going to recap what was taught in the Zoom call on data analysis, graphing, and sharing results. I'll try to make it brief since it is a recap. Last notes video we went over the first 4 steps of the scientific method. In this video and in these notes we're going to be talking about the latter steps, which is collecting data, analyzing that data, being able to draw conclusions from our experiment, and how scientists share results of their experiment. And so we're looking at how we analyze data and effectively share that with others. The end goal objectives through these notes was to be able to effectively and correctly graph a bar and a line graph, know when to use either of them, the bar or the line, be able to know what components go into the graph, what I'm looking for in Biology 1, and be able to draw conclusions based off your graph and your data. So I'm going to go to step 5 and 6, which is data collection and analysis. When you conduct your experiment, as it's going on, you're collecting data and you generally put it straight into a chart, and that helps organize your data super nicely. And so I put my IV here on the left and my DV over to the right, and I plug in my values as I get them in my experiment. So this is just a sample experiment. Once you collect your data, at that point you can analyze it. So we have 4 different ways that we look at data in Biology 1. The average or the mean is usually our go-to aspect of analysis, and that is kind of shown right here as an example. So like, let's say you wanted to find the average or the mean of the bubbles blown by the freshwater fish. You would add up all of these values and divide by the number of values that you have. So on average, the freshwater fish blew 6.6 bubbles, or you can round that to 7. I'll tell you during a lab whether you can round or not. In this case, I would say yes, because it's kind of hard to have 0.6 of a bubble. So that is generally, like I said, how we analyze our data in Bio 1, by finding the average or the mean of a set of data. You can also find the mode. That's the number that occurs most often. So in the case of the freshwater fish, it is 5. You can find the median. That's literally the middle number in a set of data laid out from minimum to maximum. And so in this case, it's 7. And then the range, we sometimes find that, and that's the difference between the highest and the lowest values. And so for the freshwater fish, that would be 8 minus 5, which is 3. All right. Now, there can be some issues with data, and so I kind of want to talk about that really quick, and that includes something called outliers. And I plugged in an example from my class from last year. Last year I had my kids finding out how many licks it takes to get to the center of a Tootsie Pop, but I wanted them to see if drinking water beforehand affected how many licks it took to get to the center. Okay, so I divided all of them up into 4 groups, and I gave them all, the first group didn't get any water, second group got a certain amount, third, fourth. However, look at group B. Do you see an outlier? So here's the data values from each kid, and here's the average or the mean down below. In this set of data, can you find an outlier? Do you know what that is? If you guess 75, you are correct. An outlier is a number that's significantly different than the other numbers in that set. And a lot of the times it's a result of error. Something happened to throw that point off from the other ones. Now, the reason I say that this is kind of bad is because it can very much throw off how your data is analyzed. So for example, when we did this experiment, if you calculate the mean for group B with the outlier, that's 75, you get an average of 292 licks. But if you calculate it without the outlier, you get an average of 336 licks. These averages are very different. And that's because the outlier throws it off so much because it's so different from the rest of the values. So sometimes it is a legitimate value. A lot of the times, though, it does result from an error in the lab. And so we'll talk more about that when we get into doing our experiments. All right, I want to move forward to why we graph. We graph because it's a great way to visually represent your data. It's a nice little shorthand, and it's a lot more organized. So let's say I showed you this data table of the height records of all the 7th graders, all the 8th graders, all the 9th graders, and I said, who has the highest average height? If you're just looking at all this data, there's no way you could sit there and be like, you know, it's the 8th graders. No, like, it's not organized very nicely. However, if I do this and I graph the averages, like a bar graph, see how that makes it a lot easier? You can definitely see, I mean, I know you probably assume the 9th graders are taller, but you can see how much taller they are based on the graph. And you can actually see how close the averages are for 7th and 8th. You wouldn't have been able to pick that out just by looking at the data table. So we graph because it's easier to pull out conclusions, it's easier to see trends, and it's a lot easier to communicate our results. All right, bar or line. And I know what you're thinking, aren't there other kinds of graphs besides bar and line? Yes, there are. There are pie charts, which show percentages. There are scatter plots, which show data trends. However, we almost exclusively use bar and line graphs in Biology 1, like 99% of the time. So that's why I spend all of my time discussing these two types of graphs. And if we ever see those other graphs, I will explain those, but I focus mostly on these in the notes. So we use a line graph to show change over time. Think time, line, both have I. We use a bar graph to display categories or amounts of stuff. I think that got cut off. So it just, rule of thumb, if you have time, you're going to be using a line graph. If you have something like categories, it's going to be a bar. All right, so in the Zoom call, I had you guys looking at these different graphs and seeing what you see similar between all 4 of them. And a lot of you said, okay, every one of them has a title. Some of you said it's in color. You know, some of them have keys. A lot of them are labeled and so forth. So what I'm looking for when you do a graph in Biology 1 is I'm looking for this acronym TAILS, okay? And that stands for title, axis, label, dry, and mix. I'll explain that. I'm looking for consistent intervals. I'm looking that you've labeled your X and Y axis with actual words. And I'm looking for correct spacing within the graph. All right, other components that may apply to the graph, I want to make sure you chose a bar or a line correctly. And if you have to use a key to differentiate your data, I want to see that you did apply that key. And I do look that you plotted your points or your bars correctly. I'm a hawk, so make sure you are precise with that. All right, I'm going to go through each acronym to tell you what I'm looking for. As far as the title is concerned, your title sounds the exact same every time, and it sounds like this. The effect of the IV on the DV. I should be able to read your title and know what you're changing and how you're measuring it. I will only accept this format for title. Only. I will take off points if it does not look like this. Okay, so I'll give you some examples. From the assignment we did the other day, the pea plants. Using that example right there, you could pull that out, and if you were doing a graph on that data, your graph would say the effect of water amount on the growth of pea plants. Water amount was what you were changing, the growth was what you were measuring. Another example that I used in the notes, Ms. Brinkman wants to know if the store brand paper towels absorb more liquid than Bounty paper towels. If you were to graph that data, your graph title would say the effect of paper towel brand on liquid absorbed. So that's your title. As far as labeling your axes, all right, I like them to be labeled, and I want to make sure that you can see this in this video. I like them to say dry on the y-axis, mix on the x-axis. Okay, and the reason I want you to label it exactly like that is because when you write dry, what you're telling me is, Ms. Brinkman, I know that this is the dependent variable. I know the dependent variable goes right here. I know it's the y-axis, and I know that another way of saying the dependent variable is response variable. So you know the dependent variable, or in other words, response variable, goes right here on the y. Okay? And mix stands for manipulated independent x-axis. Same thing. You know that the manipulated variable goes on this axis. You know that another way of saying it is independent variable. I do not want you to have your graphs with just a y and just an x. That does not cut it for me, because I know you've known since middle school that this is the y-axis and this is the x-axis. However, I want to see that you know that the dependent goes on the y and the independent goes on the x. I want to know that you know the variables going on those axes. All right, other stuff. Intervals. This is a huge pet peeve of mine. Please be consistent. I always give the rule of thumb, go by what you start with. So if you start with a 2, you're going by 2s. 2, 4, 6, 8, 10. Let's say this is your data table. I don't want this happening. Some of you take the data on the y and you just plug it in like this, where it goes 2, 5, 7, 8, 9. If you do that, the whole graph will look wrong because you don't have the appropriate spacing between those values. So make sure the intervals are consistent, and like I said, rule of thumb, go by what you start with. All right, labels. No axis cannot have a label. All your axes, x and y, need to be labeled with what the IV is and what the DV is. So in this graph here on the left, my IV is time, my DV is number of people. So you can see at the bottom of the graph, I labeled it time, and on the side of the graph, I labeled it number of people. The reason you have to do this is because I should be able to look at your graph and know exactly how you're measuring something and how what you're changing in your experiment. If you don't put number of people on the side of this graph, and let's say you didn't have a title with it, how am I to know how you're measuring? Like time, what are you measuring over time? I don't know. You have to make sure you have your IV down here, your DV over here. Same thing. Type of pet goes down here, number of people. I will always look for a label. Now I know what you're thinking. If I'm labeling my pets down here, rabbit, dog, cat, do I have to say type of pet? Yes. I need you to be in the habit of always putting the IV, always putting that DV label. And as far as labels go, don't forget the key if applicable. So if you have different variables that you're looking at and you're making a line graph and you can do colors. Some people do like little shapes for their dots. If a key does apply, make sure you remember that. Spacing is the last letter in tails. So we talked about title, axis labels, intervals, labels in general, and spacing. Spacing is super important, and I'll show you why. Here is graph A, B, and C. Okay, do you see how graph A is like really, really scrunched, and then it's like really tight up here? That's going to throw off the way your graph looks. Your trends and the way the data is supposed to be displayed will be skewed and wonky. So make sure that you're spacing this nicely. If you're working with graph paper or Excel or anything like that, that shouldn't be an issue. But again, make sure your intervals are consistent and your spacing is good. All right. So like I said, incorrect spacing can lead to misleading graphs. All right. So, draw conclusions. Looking at this, what's the busiest time for Walgreens? You need to be able to look at a graph and be able to pull out information. So in this case, I'm looking for the peak right there because it says number of people and number of people is going up. So I look at what time I have that peak, and that's at 1 p.m. Also, it says, what is the population of New York during the year 2000? So I'm looking at this graph. New York is in pink. Okay, I look down here at my year, 2000, and then I look up over at the left. This is in thousands. All right, so if I'm looking at the year 2000, it's not 8,000. It's not 8,000. It's passing 8,000. I would say maybe it's 8,800. It doesn't look quite like 9,000 to me. I would say 8,800. But again, if I were to ask you this type of question on a test or something, it would be obvious what the answer is. But being able to pull out information from a graph is what we're going to be practicing with in the assignment after these notes and in your lab for next week. All right, sharing results. Scientists, when they finish their experiment, it's very important that they share the results. The scientific community likes to compare things. They like to see if you did that experiment, what did you get? If they do the same experiment, a lot of times they'll repeat it. Did they get the same values? And they'll change around different variables. This really helps when coming to much larger conclusions, which we'll talk about in a second. When you do publish your data, when scientists do publish data or their experiments, they usually do so in scientific journals. So scientific journals are the most relevant, the most current, the most up-to-date material you can find on any scientific investigation. Usually they're peer-reviewed, so you'll submit your experiment. Different scientists in the community will review it, and then usually they'll publish it in a journal. I was lucky enough once at my time at JMU to be part of a group which had our experiment published in a journal, which was really cool. It was on a forest ecology experiment. So that was pretty neat, and it was peer-reviewed and my name was published. So it's a pretty big deal if you get published in a scientific journal. And again, it's very relevant, very up-to-date information. You can't find that type of relevant or up-to-date new information in an encyclopedia. Encyclopedias, textbooks, things like that, usually that's older reference material. And of course, scientific journals, since it is reviewed by the scientific community, it's completely more reliable than anything you would find on social media or any large media outlet like CNN or MSNBC or Fox or ABC. So this is reviewed, these are reviewed, and they are current and reliable. All right, and lastly, when we do our experiments, we come up with a hypothesis, something that we think is true. We test it. And if you get enough hypotheses kind of coming up the same, you keep getting the same consistent result in an experiment, and then other people repeat the same similar experiment and they keep getting that same answer. Sooner or later, all these hypotheses that are true lead to the creation of a theory. So a theory is sort of the next step after a hypothesis. So that's sort of the biggest difference. You may get asked that, what's the difference between a theory and a hypothesis? A hypothesis is just one prediction statement for one experiment. But like I said, if you have multiple experiments done over a long period of time, all those results and hypotheses add up to coming together with a larger conceptual idea, which we call the theory. A theory seeks to explain why something is happening, and it allows us to predict what may happen. So the theory of climate change. There's several experiments that have been proven time and time again that climate change exists, right? And so that's our theory, the theory of climate change. And because we have this developed theory, we can predict what may happen in the future if climate change continues. That's just an example. A law, on the other hand, we don't touch as much on laws in Biology 1. I think that's more of a physics game. Law predicts what will happen. It doesn't explain why, but it tells you what will happen. And it's usually mathematical. So, if I drop my phone, right, I can measure mathematically how fast that phone is going to travel down to the earth. That's the law of gravity. However, that can't explain why the phone's falling, so that's where the theory comes in. So gravity actually has a law and the theory of gravity, because the law says the phone is going to travel down to the earth this fast, but the theory says here's why that phone is falling to the ground. It's because of a force, right? So theory, like I said, big difference. Theory explains why. A law just says what's going to happen without explanation. So, just to recap here, we talked about collecting and analyzing data. I briefly went over how to draw conclusions, but we will be practicing that more in our assignments specifically. And I explained how scientists share their results. Again, the most reliable, current, up-to-date is those science journals, those peer-reviewed journals. And I touched a little bit on theory versus law, which you guys also did an Edpuzzle for, which was a fantastic video. So if you have any questions about this material, please feel free to jump in my office hours or send me an email and I can help you right out.